Okay, so today's lesson we'll talk about how the first derivative affects the graph. So if the derivative of a function is greater than 0 on some interval, then it's increasing on that interval. Okay? And if the derivative is less than 0, it's decreasing. So what happens if you think about a graph and let's just say it's, doing this. Okay? Now we know that's increasing, it's going uphill. And if you look at the derivative anywhere on here, and you draw that tangent line and you look at the slope, okay, that slope is going uphill from left to right. So that means the slope is positive, correct? So the first derivative would be 0 there. On the other hand, or would be positive there. On the other hand, if you have a function that's decreasing and you draw a tangent line anywhere on there, that tangent line is heading downhill, so the slope is negative, right? So positive slope increasing, negative slope decreasing. Now let's take a look at a couple of examples here and see kind of how that works out. So suppose we have this function x squared plus 4. We want to find the intervals where it's increasing and decreasing. So it's kind of easy enough to see that with this graph, the heck? It's going to look like this, right? So where we need to figure out really is where is the derivative equal to 0? Because that's where it's flat, and then we think on either side of it, is it kind of increasing, decreasing, when's it less than 0, however you want to do this, right? So if we look at the derivative here, that's just going to be 2x, right? So where is it decreasing? Well, we could look at the inequality, right? Where is 2x less than 0? And we solve that and say, okay, well, it's decreasing on the interval where x is less than 0. If I wrote that out, we could go with negative infinity to 0, right? And the next question is, where is it increasing? Well, then 2x has to be greater than 0, or in this case, x is greater than 0. So that's from 0 to infinity in an interval notation. That's kind of easy to see, right? I mean, it's going uphill on this half of the parabola, and that's from 0 on over. And then on this half of the parabola, it's headed downhill, and that's from negative infinity to 0. So that was our easy example. Let's try something a little different here. And we want to look at the graph of x plus 2 cosine of x. Okay, so that has kind of this weird look to it. Okay, now I'm not going to draw an accurate graph here, just kind of an ugly sketch. Okay, so it kind of looks like that. Notice we've got several spots where it's increasing here, it's increasing here, it's increasing here, but then turn around and on these little small sections in here, it's going downhill, is decreasing. So let's find out where those spots are, right? So let's look for increasing. If I can get this thing right, I think I would have learned my lesson after all this time. So increasing. So the derivative, f prime of x, is 1 plus, 1 minus 2 sine of x. So we want to know, when is this thing greater than 0? And we could do then add 1 to both sides. Or subtract 1 rather. Then when we divide by that negative 2, we get sine of x has to be less than 1/2. Okay, so again, let's go back to the unit circle stuff. Okay, so our unit circle is here. Sine is the y coordinate. So we want to know, when is sine less than 1/2? And the y coordinate 1/2 would be around here, so it's got to be less than that. So where is the ordered pair where we get a 1/2 for the sine. I'm giving you a moment to think about it. So I believe that is when x is pi over 3. Okay. And then it's all this bottom half down here, all of these angles, right? Because we want all the ones that are below that. So we could write that in several kind of ways. Since we have kind of infinitely many of these intervals, I think we could start, say, well, just write them out if you want to. Okay, we're going to go from, I think easiest will be to start from here and work our way around and see what happens, because then we can go full circle again, right? So if this is pi over 3, and we go kind of backwards, what's this one going to be over here? Well, this reference angle in here is pi over 3 as well. So if I kind of want to figure that out, we're going to do kind of pi minus pi over 3. And maybe I'm kind of going about this the long way, because I'm just thinking about these reference angles. That would be, what, 2 pi over 3. Now the 2 pi over 3, though, is this piece here. So, yeah, I went about this the long way. So if I want to make that negative, we're going to do 2 pi over 3, and we're going to go backwards full circle. So that's 2 pi, which would be 6 pi over 3 if I get a common denominator. So negative 4 pi over 3. So our interval to start with is going to start at that negative 4 pi over 3. Let me erase that little stray mark there. Negative 4 pi over 3, 2, and then we're going to go to pi over 3. All right, union, and then the next interval, everything would be full circle, right? Okay, so I think, that kind of goes on and on and on. But since we're going full circle each time, where did that come from? 4 pi over 3 plus 2k pi, because we want to go full circle there. And we're going to end at pi over 3 plus 2k pi. So it's increasing on all of those intervals. Now, where is this thing decreasing? Well, we can see easily enough if we just switch that inequality, it's going to be decreasing on the top part of it. So it's between pi over 3 up here and 2 pi over 3. So if I want to switch that and say, okay, well, it's decreasing on, we'll start at pi over 3, and then again we can go full circle. And then it goes all the way up to, let's say, 2 pi over 3, and then around that circle again. Okay, so this is one of the more complicated ones, and I have to picture that unit circle to see where it's less than a half and where it's greater than a half and stuff like that, okay? But again, make sure that you have a copy of that unit circle somewhere to help you out with some of these trig functions and stuff. So, moral of the story is increasing when the derivative's greater than 0, decreasing when it's less than 0. Okay? Now, we can also use the first derivative test in this idea to find the maximums and minimums. So let's suppose we have a continuous function and we look at the critical numbers. Now, remember last section we talked about the critical numbers, and that's where the derivative is equal to 0. Okay. So the first rule says if it changes from positive to negative, we have a maximum. So if it's positive, it's going uphill. And then if it changes to a negative and goes downhill, clearly that's going to give you, why did it move on me and disappear? A maximum, right? Rule 2 says if it's headed downhill and then somewhere it turns and heads uphill, then at that spot where it changes is a minimum. So first derivative, if it's positive to negative, gives you a maximum. If it changes from negative to positive, it's going to give you a minimum. And then if it doesn't do either one, then it gets us what, it's neither one. It's like an inflection point or something like that, which we'll get into in the next one. But let's say if it's positive and then it stays positive, it still goes uphill, even though the derivative might be 0 there, and you might have a critical point, it's not a maximum or a minimum. But remember, that goes back to that Fermat's theorem from a couple of videos ago. Just because the derivative is 0 doesn't mean you have a max or min. Something's going on, and those first two little rules tells you when it's a max and min. So it has to change from positive to negative or negative to positive to get a maximum or minimum. So let's look at a few examples here. Okay, and some functions we've already done. So we already had the graphs for those and stuff to think about, right? So, this graph, this parabola looks something like this. So I know looking at the graph, I'm going to be finding a maximum or minimum. Hey, I forgot to change my question. Find the local min, max. Remember, they might just say extrema. Could be worded in any of those ways. So the first thing is, when you're looking for the maximums, find the critical points. So we solve the derivative equal to 0. Say, okay, well, we only have one critical point, and that's where x equals 0. So think about a number line, and this is going to be a good habit to go ahead and start with, because I'm going to rely on it pretty heavily, especially come the next section when we start sketching graphs and stuff. So anywhere in between the critical points, you can just pick any test number. So I'm going to look at -1 and 1 just because they'll be easy. Okay? If I look at the derivative f prime of -1, that is 2 times -1, which would be -2. So I know it's decreasing on this interval. So I know my graph is headed downhill anywhere from -infinity to 0. Okay? Now, on this other interval, if I test it and we do f prime of 1, that's just 2 times 1, which would be 2. So I know that function is increasing. And if it switches from decreasing to increasing, that tells me we have a minimum. So we have a minimum at x equals 0 because it switched from decreasing to an increasing function. Now if we go back to our super cool funny graph, and again, I cut and paste stuff and then forgot to change the wording. Find local extrema. So we had that f prime of x was 1 plus 1 minus 2 sine of x. And where our critical points are, where it's equal to 0. So we get 1 minus 2 sine of x equals 0. So sine of x needed to be 1/2. Now, remember that was at all of the pi over 3 plus 2k pi's and 2 pi over 3 plus 2k pi's. So we had all kinds of intervals where this thing is going to be increasing, decreasing. So you know what? Let me change this question a little bit and say, let's find the maximum, minimum, or find the local extrema in the interval from 0 to 2 pi. So what that does is just, I'm taking out the going around the circles there. Okay, so in that interval, that's what we have. And remember, this function did this number. Kind of a very hilly climb there. And so on our number line, then what I want to think about is then just labeling the critical points So we have pi over 3 and 2 pi over 3. Now notice we have actually 3 intervals here. We have this one, this interval, and this interval. And I need to pick a test point in each of those. So in my first interval, I'm going to pick something that's less than pi over 3. So you know what? I'm going to go with, let's be crazy, and use a 0. Okay, so 1 minus 2 sine of 0. And on this part, I mean, if you wanted to grab a calculator and do it, sine of 0 is just 0. So that is just going to equal 1, right? And then that tells me it's positive, so I know my function at this point is headed uphill. It's increasing. Now when I look in the next interval, I need to pick something between pi over 3 and 2 pi over 3. So you know what? I'm going to test pi over 2. And I tested 0 over here, just to label them, okay? Now, the reason I picked pi over 2 is if you think about that unit circle, the points that we have that we're interested in are right here and here. And pi over 2 is just straight up. That's an easy one to deal with. So f prime of pi over 2, just for the sake of room, I'm going to write below here is 1 minus 2 sine of pi over 2. Now, sine of pi over 2 is equal to 1. So we get 1 minus 2 times 1, which would be a negative 1. So again, I know this thing is negative, that derivative, so it's headed downhill. And now I want to pick something bigger than 2 pi over 3, so I'm just going to go test point with pi, because that would get me over here. So far I've used 0, pi over 2, and pi, and I'm just picking things that are easy to evaluate. So f prime of pi is 1 minus sine of pi. Well, that's 0 again, so we're back to having 1. So I know it's increasing here. So at pi over 3, we have a local minimum. And then at 2 pi over 3, we have a local max. So I just wrote those backwards. I'm looking at my graph and I'm looking at what I wrote. This one's the max because it went from increasing to decreasing, and this one is the min. But you know what? This is exactly why I like to sketch out my graphs, because I start to write the wrong thing, but I look at the picture and they don't match, right? Because I look at that part and it's a hill. Pi over 3 comes before 2 pi over 3, so why was my hill before my valley? And that just clued me in that I wrote something down wrong, okay? So I always think it's really valuable to have picture of the graph for that reason. All right, so let's do one more kind of easier one, okay? And that's f of x equal x cubed, and let's find out where it's increasing and decreasing. So, and we were supposed to find Extrema, okay? So where's this derivative equal to 0? Well, when x equals 0, and that's the only critical point. So I'm thinking about that silly little number line again, and I want something in this interval, and then something in that interval. I'm just going to pick things that are easy, like, oh, I don't know, -1. What's a -1? 3 times -1 squared. Okay, that's going to be 3. If I look at f of 1, that's 3 times 1 squared, which is 3. So you'll notice in both cases it's increasing. Okay, and if you graph the function, oh, it looks something like that. That tells me, since it doesn't change, no local min or max. Okay, so there's an example when you get the derivative equal to 0, but on either side it stays the same. Even if it's both decreasing, still no min or max. So our first derivative test that says that the sign of the derivative has to change to get your min or max. All right, there's my note to end the video. So next up is going to be about the second derivative.